We always have discussions about what should we do as topics for these webinar series. And we've covered a lot of things specific to heat pumps in the past webinars. So we said, well, what about, common errors that are occurring in the field with both water to water heat pumps as well as air to water heat pumps? So we've identified 10 that we'll refer to as either design or installation issues to avoid. These are things not to do rather than telling you what to do. These are things not to do. So we're going to look at as found conditions with some photos. We're going to describe what's wrong and why is it wrong? What's the fundamental concept that's being violated here? And then we're going to also talk about how to prevent the situation if you're in a design mode. Obviously there are details that you can use to prevent problems, or if it's already been installed, what can be done to correct the problem. And sometimes the problems are obvious. We had one of the hardest winters in upstate New York in the last 40 years. And it's easy to go around and see condenser units outside that are buried, in this case, half buried, but some of them were actually fully buried in snow where nobody was taking care of it. That's a pretty obvious error. But then there's others like this. I will tell you there are problems with what you're looking at there right now. We've got two heat pumps in parallel. They're running as a stage system. We're going to come back and visit this later. And as they say, sometimes the problems are not obvious, and sometimes the problems are not just related to the heat pump. They're fundamental design errors based on the hydronic layout. So again, we're going to be using the term hydronic heat pump, and that would refer to any heat pump that delivers heated water or chill water for cooling to a hydronic distribution system. And that includes both air to water heat pumps as well as water to water heat pumps. And we can kind of lump them together in a lot of cases because the balance of system design, this is everything but the heat pump. Oftentimes they're identical, the balance of system designs, whether it's a water to water heat pump or an air to water heat pump. So what are those considerations? Well, many of them have to do with temperature. What are the heat emitters that are going to be used with these heat pumps? Were they designed around higher temperatures than the heat pumps can provide? And another area is flow, the flow rate that these heat pumps require relative to what might be required with, let's say, a cast iron boiler. We have to respect both the temperature and the flow operating conditions on either type of heat pump. We also need to understand how the performance, the thermal performance and the efficiency of the heat pump depend on both the air temperature in the case of an air source heat pump, the source water temperature with a geothermal heat pump, as well as the water temperatures that we're asking these heat pumps to produce for the load. So where do these problems originate? Well, some of them are just misapplication. I'm sure most of you that are watching this today know that an R410A heat pump really can't produce 170-degree water, but there are people in the industry that don't realize this. So we, again, need to look at what is the refrigerant, what is the machine rated to produce, how does its thermal performance vary with water temperature. So as I mentioned earlier, many times the issues are based on some fundamental missteps when it comes to the hydronic design or the hydronic installation of the system. And, here's a spattering of photographs that have collected over the years. Putting the most efficient air to water or water to water heat pump into any of these systems is not going to lead to good results. Where we've got tubing just clipped to the bottom of the subfloor, we've got aluminum foil being used in place of aluminum heat transfer plates. These are just poorly conceived systems. And again, most of you would understand this, that just dropping a heat pump in isn't going to fix the existing baggage, I'll call it, in these systems. So let's start with one. We don't want to just think of these systems as a situation where we have an existing system like what you're looking at there. We've got 3 zones of baseboard heating. We've got a zone that goes through an indirect water heater, and we've got a cast iron boiler. We don't want to assume that we can just cut out the cast iron boiler and drop, in this case, a water-to-water geothermal heat pump in its place. Again, the water temperature requirements of the heat emitters, the flow, especially if there's only one zone operating, these are all going to ultimately reflect back on, can the heat pump provide that performance? And when it's very high temperature water that's required at design load, uh, today's heat pumps really can't provide those temperatures. So we don't want to do that. Again, the flow resistance, moving fluid through a heat pump, heat exchanger, the condenser of a heat pump in the heating mode, that requires more pumping power compared to what's required with cast iron boiler. And as I mentioned, water temperatures from the heat pump may be too low. And be especially careful with zone systems, heavily zoned systems, where the flow rate in the distribution system could go much lower than the required minimum flow rate in the heat pump. So again, how do we fix something like that? Well, we have to think system-wide rather than just the heat source. And we want to think about, what can we salvage from the existing system? There may be a large portion of the existing system that can be salvaged, but we always have to respect that operating temperature and flow rate conditions that are required by the heat pump. I just want to show this. This was a retrofit of an Enertech AV system. And over here on the left, what used to be here was a propane-fired furnace. And you can see the existing ductwork up above. The ductwork was examined. It was deemed suitable for the airflow rates that the air handler would provide. So this is an example where the existing duct system was salvaged, and it was supplied now from a new air handler, and that air handler is supplied from the Enertech AV system. Now, it says, don't starve a single-speed heat pump for flow. So let's assume that the heat pump that's shown in this drawing here is a single speed. It's just on or off as a compressor. And over on the right, we've got 6 zones. Each zone has a zone valve in it, and those zone valves all are controlled by independent thermostats. So we have to make the assumption here that we could have just one small zone calling for heat. Maybe it's just a zone that warms a radiator in a bathroom, or maybe a floor circuit in a bathroom in the morning. And we turn that zone on, the circulator turns on. The circulator might or might not be a fixed speed circulator. If it's one of the newer circulators with the variable speed motors, its speed could adjust to the fact that there's only one zone open. And at that point, we've got a very minimal flow rate going back through the heat pump. The heat pump is unable to transfer the heat that it is producing to that low flow rate stream going through there. And typically that's going to cause a high head pressure condition in the heat pump. So again, watch out for flow restrictions. You have to look at that existing distribution system. And we will talk about methods for accommodating that with a single speed heat pump. Excuse me. So when you have a single speed heat pump, and again, I want to emphasize a compressor that just turns on or off, and that could be in either a water-to-water heat pump or an air-to-water heat pump, we need to have some kind of a buffering mass in the system. If it's a low thermal mass distribution system, like maybe fan coils or baseboard that are being serviced by the zone valves, we're likely going to use water as the thermal mass. If it's a zoned high mass distribution system, like a radiant floor slab, we'd have to look at that and see there may be enough thermal mass in the individual zones of that slab so that we don't necessarily have to bring a buffer tank into the picture. But again, I wanted to show the concept. In this case, it's called a 3-pipe configuration. It's actually a configuration I really like when we're using single speed heat pumps. Basically, the flow that comes out of the heat pump Some of that flow can go to any existing or operating zone in the system. The balance of the flow would go into the buffer tank. So we're not starving the heat pump for flow with this kind of a system. Now, Intertech makes both air to water as well as water to water heat pumps that are true variable speed heat pumps. Justin Job talked about the WV unit in last month's webinar. If you want to go back and look at the YouTube on that, these heat pumps have control of the compressor speed as well as the flow rate, and they don't require buffer tanks. So again, I want to distinguish between a single speed on off heat pump versus a true variable speed heat pump. Now, another one that we see more often than we would like would be don't install an air to water heat pump on a ground pad only a few inches above grade. Now, this over here on the far left, that's an air conditioning condenser unit. It's sitting on a couple blocks that are literally right at grade level. You can see the leaves accumulating around it. In the summer, you would have grass clippings, you'd have insects, snakes, and so forth around that. In the middle here, we've got a unit that's on a very shallow concrete pad. That was installed in a warmer climate where they really don't get much snow. It probably would be okay from the snow standpoint, but still getting it above grass clippings, getting it above just anything that is on the lawn is going to help keep that coil clean. Here's a heat pump that's actually on a stand. That stand is about, I'd say it's about 16 inches tall. This is in upstate New York. This was a unit that was completely buried in snow this winter. Over here on the far right, you can see another picture. I literally dug that unit out of that snow with a shovel. And you can see that the line sets would have been covered with snow. You can see some damage to the channel that the line sets were routed in. Obviously, if that unit is even partially covered with snow, you're not going to get the right airflow going through it. So if you're in an area that experiences the potential for some deep snow or drifting or snow that might be shoveled off a roof and literally roll back and cover up the heat pump, these are all things to think about during the planning process. Okay. So what's the fix? To get the unit up in the air. Over here in the upper right, those are actually two photos of the same heat pump. You can see that stand would normally hold that, well, it would hold that heat pump about the base of it about 3 feet. That's in an area that gets a lot of snow. This winter, the snow got pretty close to the base of that heat pump. It was probably within a little less than a foot. Over here in the lower left, you can see a couple of the Intertech outdoor units. Intertech does have a 12-inch stand. They also make an 18-inch stand that can suffice in many locations. Another thing to think about is the condensate drainage coming out during defrost. During defrost, these heat pumps can drop easily a quart, maybe even sometimes a little more than a quart of water. And this photo that has the 3 red rectangles in it, this is up in northern Canada. And what I want you to see in these rectangles are these, I'll call stalagmites made out of ice. That is not water that was leaking from the heat pump. It's water that would drain out during defrost. Now imagine those heat pumps were just 2 or 3 inches up above grade on a concrete pad. That water that drains out of the unit during defrost will flow out maybe an inch or two and it'll freeze. And I've actually seen this happen. It'll create what I'll call an ice bathtub around the base of the heat pump. And then as more defrost water accumulates, it can actually come up and freeze on the coil. So we want to get those units up and make sure that there's nothing that's inhibiting the water drainage from the bottom. Here's another one over on the lower right. You can see this is this water stain on the grate here. This is from the water that's drained out during a defrost cycle. And that unit is up high enough that, even in the wintertime, that water can drain out of there. All right. Now, this photo you're looking at, this is about 10 miles from where I live. And where the building was located, this last winter, there were over 200 inches of snow. It's an industrial building. It's got a metal roof. I'm not sure what the thinking was of putting these 4 units outside and then running this ducting in through the wall, but you can actually see above one of those, heat pumps that the fascia on the overhang's already been ripped off, and if you look carefully, you see that one of those heat pumps is brown, the other 3 are green. That's because one of them was probably already damaged. Imagine 2 feet of snow, maybe a day in late February, early March, when it starts to warm up, 2 feet of snow come sliding off that roof and come directly down on those heat pumps and the ducting. So we've got to be careful about that. And again, any type of a metal roof, you typically do not want to put any kind of a heat pump unit, or if it's just an air conditioning condenser unit, you don't want to mount it where you could have snow sliding off the roof, or even in the summer, just water coming off that roof in a heavy rainstorm and dripping or flowing at a higher flow rate down onto that heat pump. When I think about where icicles could break off and land on that heat pump. And, in putting the slides together, went out and looked to see, does anybody make a roofing system? And there are some temporary, I'll call them roofing systems for outdoor units. This one is a fabric roof. It probably would be fine for rain, but take a look at the slope on that roof and imagine snow sliding off of that roof, or ice. That comes down with a lot of force, and that could easily break that roofing structure. So again, when you're out contemplating where to put that outdoor unit, think about snow, ice, and rain coming off the roof. And if you've got to put it under an area where snow is going to slide off, you're probably going to have to build some kind of a roof over it. So again, here are some examples. Here's a couple units that were put in under a deck that would protect them from, at least from snow falling. Here's another outdoor unit that has an overhang over it. There's not a lot of water really coming off of that particular overhang. Here's a couple units. This is kind of nice, where they actually created an alcove in the building. Now, obviously, that's a unique situation where they knew they were going to put air to water heat pumps in, so they created this little sheltered area, raised the heat pumps above grade, and there's a roof area over the top. Here's a photo. This is an air to water heat pump that's mounted outside. You can see what's already happened here. This metal roof has shed its snow. You can see the pile of it. So just imagine that pile of snow came down on that heat pump. If that heat pump was mounted right here, that's what would happen. And here's another photo. This is that elevated mounting, but you can see there's a gutter installed over this. It's a relatively steep roof, but it's a shingle roof. So typically snow doesn't slide, but rain will come down that roof. So there's a gutter that takes most of that rain and channels it away from falling on the heat pump. So most of these things are just common sense, looking at those roof slopes, where they drain. If you're going to put a unit under a roof overhang where it's likely to get snow or ice coming down, you need some kind of a sturdy structure to protect it. Okay. And at minimum, if it's a shingle roof, try to keep the rain off it with a gutter. Okay. All right, let's go back inside. So here's some photos just to show what can be found inside a hydronic system, especially an existing system. You can see here, it looks like somebody's been panning for gold, but those are just copper flakes, copper chips, and dirt that have been flushed out through the bottom of a dirt separator. This is a heat exchanger out of a modulating condensing boiler. Look at the accumulation of just scale. That's because of very hard water was put into that system. Down below here in the middle, these are just accumulations, iron oxide accumulations inside a cast iron boiler. So if you're retrofitting a heat pump into an existing system where there is a cast iron boiler, if it's been in there for a while, if there's other ferrous components in the system, circulators, iron pipe, so forth, you could have this material in there, and you don't want that to go into the heat pump. Over here in the lower left, that's the rotor out of a circulator that has a permanent magnet installed in the rotor. All the modern circulators with the ECM motors have these permanent magnets, and they're very strong magnets. And what you're looking at is magnetite. This is a very fine uh, particulate that's basically an oxide that forms on the iron in the system. And you can see that magnet attracts it, and that'll actually cause a rotor to stick. And the torque, the starting torque on those ECM motors, those motors have a pretty high starting torque relative to standard circulators, but in this case, they were unable to break that free. So again, it's a hydronic detail. It's not really specific to heat pumps, but it's an important consideration if you're designing a new system and if there's any ferrous metal in it, but it's especially important if you're retrofitting. So there are hydronic detergents on the market. Fernox makes a product called F3. There are some other products on the market. These are basically, again, they're designed to internally clean the piping. It's fairly easy to do this. You can set up a bucket, put some of this in, it's dissolved in water, and you circulate it for perhaps an hour through the system, and it will dissolve and bring back some of the scale in the system. I'd recommend a good magnetic dirt separator in any retrofit application, as well as new applications. But again, I want to stress retrofits where the magnets that are in this device will collect the magnetite. And those magnets actually can be removed from the separator without draining, without actually having to isolate the separator. And you can see there's a valve on the bottom that you could drain this out. And I've watched these drain, and at first you'll be amazed how much black water can come out of a system. That's what you don't want in that heat pump. And then finally, I'd highly recommend when you're using antifreeze, if you're setting up one of the air-to-water systems and you're going to use an antifreeze solution, the chemistry between the existing water in the system or even new water and the antifreeze needs to be correct. And the best water to mix antifreeze solutions with is demineralized water. And what a demineralizer does is it strips out some of the salts that come with groundwater, calcium, magnesium, and so forth. These are dissolved ions that are in the water. They can be passed through these cartridges, and these cartridges hold resin beads that are specifically created to pull out the salts that are in the water. And what you're left with is almost perfectly pure water. You don't need to demineralize it to completely to 0 parts per million, but typically we'd like to see the water down to around 10 to 30 parts per million total dissolved solids. And then you mix it with the antifreeze. And now you're creating a nice compatible chemistry for the water, and you're introducing it into a system that has been internally cleaned. Here's another one. If you're bringing piping in through an exterior wall, and if that heat pump that is on the outside of the wall is going to be operated in cooling mode, we want to think about any kind, especially copper pipe. If it goes through an insulated wall cavity in the summer, if it's an uninsulated pipe, it's going to have condensate form on it. If you go through a wall that has fiberglass or cellulose insulation on it, that's not a vapor barrier. That's not going to insulate that pipe and prevent condensation. And over here, this is actually, it's not a heat pump, but I just want to show you what it looks like when you have a component that's leaking inside a fiberglass wall. You can get mold and mildew forming inside that wall. And again, I put a graph in here if you're wondering, what combination of air temperature and humidity will produce a certain dew point. You can use that graph, but I can tell you for sure that in the summer when that heat pump is operating and cooling, you're going to hit the dew point on that piping. You're going to be well below the dew point. So how do you deal with that? Well, I'll show you one way that we've dealt with it in the past. So I'm going to start with this. This is an air-to-water heat pump. You can see the flexible hose connections here. I put an arrow on there and I put a note. It says to allow some offset. You can see there's a little curvature in those hoses, We don't want to come straight out with those hoses because two things. We want to have some flexibility there. That heat pump can move outside. If you have a 30 or 40 mile per hour wind gust against that heat pump on just about any stand, it's going to move a little bit. It's going to move back and forth. And we don't want that strain to be on the piping. So we want a little bit of offset in the piping. So I'll show you how the flex hoses that were outside, how they were insulated in this case. What was done was to take a hole saw and go through the wall, and a piece of 2-inch PVC DWV pipe was used. The hole saw created a hole a little bit larger than the outside diameter of that pipe. So where it actually went through the wall on the outside and the inside, the installer wrapped that with some friction tape. So there was a nice tight fit there. And you can see the 1-inch copper tube goes concentrically through that sleeve to the inside. And then that gap between the outside of the tube and the inside of the sleeve was filled with a foam sealant. That's just a can of great stuff that you would buy at Home Depot, for example. Now, the foam will expand as it cures. It'll push out, but you can trim that off with just by taking it. Just take a hacksaw blade, take it out of the hacksaw, and just gently cut that foam and peel it back. You can bring the insulation right up to that. You could even run a bead of caulk right where that insulation joins up to the wall. And same thing on the inside. The foam expands where the pipe came through on the inside. You can trim that off later on. And I just want to show you, here's another product that's on the market. This is a 2-component urethane. When you push that syringe, you're basically mixing a hardener with the polyurethane. And if you have an especially deep cavity, that ensures that that material is going to cure into a solid all the way through there. Here's another one to be careful about. Oftentimes, existing hydronic systems will include an indirect water heater. You can see here's a cast iron boiler, and one of the zones goes over to this indirect water heater. And to understand where the potential problem comes from, you have to think back when these indirect water heaters were created. They were entering this market, probably about 40 years ago now. And that was an era when boilers were pretty much the dominant hydronic heat source. And most of those boilers in that time could easily create 180, even 200 degree water. So the manufacturers of these tanks looked at, well, how big a heat exchanger, an internal coil heat exchanger, do we need if we specify we need at least 180 degree water? And you can see the coils in these tanks really aren't very large. In some cases, the coils use thin copper tubing. In other cases, just smooth outer surface stainless steel. And I threw a couple clippings here from one manufacturer's rating just to show you that the notes show all ratings are based on 200 degree boiler water and 50 degree cold water. So yes, we can get good heat transfer when we have such a large temperature difference between the boiler water going through the coil and the cold water at the bottom of the tank. That's not the case, though, when we have a heat pump. And one of the things you want to realize about any kind of a coil heat exchanger that's immersed in a fluid like this, they rely on what's called natural convection to remove heat from the outer surface of the coil and transfer that heat into the water in the tank. Natural convection is a much weaker form of heat transfer compared to forced convection. Forced convection is what you have when you have a circulator pushing the water through. What is called the boundary layer between the bulk of the water flow and the surface that we're trying to drive heat through is much thinner when we have forced convection. So the bottleneck in heat transfer is not the inside of the coil, it's the outside of the coil. And if we connect a source device that, let's say we produce 120 to 130 degree water, we just don't have the heat transfer rate. We simply don't have the physics to transfer heat away from that coil at the same rate the heat pump is producing heat. So what's going to happen is the fluid in the circuit between the indirect tank and the heat pump is rapidly going to rise in temperature, and the heat pump's going to shut off on some kind of a safety limit, and it could short cycle. So be very careful when you're dealing with especially existing indirect water heaters. What kind of coil is in there? And the reason I say especially retrofit, the two photos you're looking at here, these are nice, clean heat exchangers. They're brand new. A tank that's been in service for a few years in an area that may have some hardness to the water, it could have calcium scale or magnesium scale on that coil. That's going to further reduce the ability to transfer the heat away from that coil. Now, uh, again, we're going back to the Enertech AV system here. When that system was designed, the tank that was being used here is a Turbo Max tank, and there's a cutaway of that tank there. You can see there's a lot of internal surface area. These tanks have much more surface area than a standard indirect tank, and they are compatible with the water temperatures that the AV system can produce. And again, here's a schematic. You have the outdoor unit, the piping comes to the indoor unit, and there's a dedicated circuit that goes over to the TurboMax indirect to create the domestic hot water. So, uh, again, this is a specialized tank. It was selected based on the rate of heat transfer and reasonable water temperatures that the AV system could provide. Now, here's another one, and we've seen this happen. I've seen it happen with boilers, but I can certainly imagine it could happen with heat pumps. You don't want to connect multiple hydronic heat sources in series. There's nothing but downsides to doing this. So here we're looking at a ModCon boiler that is getting the return water. That's the blue line you see here. We're going through the boiler, and then in series, we're going through the condenser in a water-to-water heat pump and then out to the load. There's a lot of things wrong with this, okay? If the boiler was operating, the water leaving the boiler going into the heat pump is definitely warmer than it would be if the cool water came directly back to the heat pump. We have the pressure drop of both the boiler heat exchanger as well as the condenser heat exchanger and the heat pump in series. That's going to impair the flow rate. The circulator in this case, in general, we don't want to pull, and I use that word with quotes around it. We don't want to try to pull heat through high pressure drop devices. This can lead to cavitation in the circulator. Now, here's another one. When only one of those heat sources is operating, the other one, because it's always in the flow path, is just acting as a heat dissipator. You're going to have jacket heat losses. You're going to have heat losses from any components in an inactive heat source that you're pumping warm water through. And here's another thing. If you had to remove one of these for service, you're going to have to come up with some kind of temporary piping. Excuse me. Because there's only one flow path here. Okay. And then finally, if the heat pump was providing chill water for cooling, you're going to pump chill water through the boiler, and that's just going to cause condensation inside the boiler, which you don't want to do. So again, stay away from series piping with multiple heat sources. Here's one fix. This is a parallel situation. The boiler and in this case, the water-to-water heat pump are set up in parallel. Either heat source could operate by itself, or they could both operate together. Each one of them has its own circulator with a check valve. The check valve's important because without the check valve, you'll have reverse flow through the inactive heat source when the other heat source is operating. And then you want some kind of isolation and purging valve on the pipe leading from the heat source back to that common header system. Okay. So again, they're in parallel. Both receive the same low temperature water. So you're going to have the best efficiency on both of them. We talk about the check valve. Each of them can operate independently or they can operate together. And each of them could be isolated. And if necessary, they could be removed for service without taking the other heat source out of operation. Here's another way to combine. Again, this is the Enertech AV system in what's called direct-to-load piping. Justin talked about this, and we've talked about it in past seminars. Rather than put them in parallel, the boiler is being tied into the piping coming in from the heat pump using a pair of closely spaced T's that provides hydraulic separation. So if the boiler is not operating, the flow basically goes right through there. It doesn't go up and dump heat through the inactive boiler. So that's another way to do it. The current version of the AV can control the boiler either on off, or it can use a 0 to 10 volt signal to cause the modulating condensing boiler to vary its firing rate so that the amount of heat being added is just as necessary to get the proper supply temperature. And again, you'll see the heat pump in this case is always receiving the coolest water. We're going through the heat pump first. If the boiler needs to operate, it takes the water from the heat pump and boosts its temperature up. Okay. So again, we've talked about all those, the closely spaced T. And again, I'll just stress that circulator should have a spring-loaded check valve in it. Those check valves need about half a PSI to open. The reason the check valve is in there is to just stop any type of flow migration from the closely spaced T's up into the boiler when the circulator is off. Okay, now here's another one. You'll see a lot of schematics if you start looking at how air-to-water heat pumps can be interfaced to both heating systems as well as domestic hot water. One of the common things you'll see is a three-way motorized diverter valve. And the idea is pretty simple. If we need to heat the domestic hot water, the diverter valve is going to take the flow coming from the heat pump and send it to that tank. If we're operating in cooling, the diverter valve is going to send the chill water up through the coil in the air handler. That's all fine. But what happens during mode switching? Let's say that we're in a mode where we're heating domestic hot water, and then we satisfy the temperature we need in the indirect tank, and then we immediately switch over to cooling. Okay. The problem is that the piping from the diverter valve back to the heat pump, as well as the piping from the tank back to the heat pump, still has hot water or hot antifreeze in it. And if we immediately direct that flow back up to the coil in the air handler, we're going to get quite a burst of warm air, at least for maybe a minute, minute and a half, while that circuit cools down. And it's almost guaranteed you're going to get a callback on that. Somebody thinks we're turning on the air conditioning. Why should we experience this blast of warm air, even though it might only last a minute? And if you're switching from cooling into domestic hot water heating, it's a similar problem in reverse. We have chilled fluid in the piping leading to the heat pump. The diverter valve now is going to route that into the indirect. In a sense, we're going to rob heat out of the indirect by sending chill water into it. So how do you get around that? Well, the way Enertech has fixed this, basically avoided it right from the design of the system. They're using two valves. One valve opens on domestic water heating. Another valve would open on either space heating or cooling. When the water temperature leaving the heat pump is at a temperature that is not suitable for the load that it is going to be directed to, both of those valves could be closed. Well, we still have to have flow through the heat pump while we're waiting for the temperature of the fluid to adjust. That's where the bypass valve comes in. This is a pressure activated bypass. The flow would basically come in here. Since these valves are closed, it would go through the bypass and basically right back out to the heat pump. So that's a clever solution, and it prevents those hot slugs from the air handler or the chilled slugs going into the indirect water heater, but it still allows the flow rate through the heat pump to be where it needs to be while the temperature of that fluid in the piping is changing. Okay. Okay. Here's another one that, again, you think about these things sometimes after you've seen the installation, but when you have closed dryer vents or vents from modulating condensing boilers, both of those can produce a lot of steam. And if we have a heat pump mounted 4 or 5 feet away from a vent like that, with the right wind conditions, we're basically just going to bathe that outdoor unit in this very moist air. And that's just going to create more and more need for defrosting. So here's a coil on an air to water heat pump over on the far right there. And you can see that coil's completely frosted up. That unit is about to go into a defrost. And we want to minimize defrost because defrost is essentially scavenging heat from inside the building and sending it outside to melt that frost off. So the less defrost cycles we can go through, the better. So again, as you're evaluating a site for potential placement of a unit like this, look for dryer vents, look for venting, especially from a ModCon boiler, because just if you're trying to put the heat pump reasonably close to where the mechanical space is in the building, and if there's basically a ModCon boiler already installed, or for that matter, even a furnace that is a condensing furnace, there's a good likelihood that that venting is pretty close to where you might initially think you want to put that heat pump. But you don't want to do that. You want to make sure that you get it away from potential plumes of moisture like this. Okay. Now, here's another one. I've seen this many, many times. When a conventional boiler is operated at conditions that cause sustained flue gas condensation. In the lower left, that's a copper tube boiler. You can see the scaling that's taken place in there. In the middle, inside that rectangle, that's a hole right through the vent connector pipe. And I'll tell you, that vent connector is only about 6 months old. So when its first heating season, there was enough flue gas condensation to cause a corrosion right through that vent. Here's another one, and this is something I've learned to do over the years. You go in and look at an existing boiler. I always like to look at the condition of the vent pipe. And I also like to look at the floor under the vent pipe. And you can see the vent pipe here is scaled up pretty good. And there's evidence of a puddle, water that has dripped from under that connection onto the floor. Well, this was a boiler that was installed for several years, and it supplies radiant floor heat. And there was no provision to boost the inlet temperature to that boiler so that the boiler could operate above conditions that would cause sustained flue gas condensation. And then there would be a mixing device of some sort farther out into the piping that would reduce the water temperature. So yes, we could operate the floor at 95-degree water, but we don't want the boiler to have, let's say, 90-degree water or even 100-degree water coming back into it. A reasonable number for, especially for gas-fired boilers, you want the return water to be at about 130 minimum. That is warm enough that you won't create sustained flue gas condensation on the boiler's heat exchanger. So again, as you go into an existing system where there's a boiler, remember that with a heat pump, that distribution system is going to operate at lower water temperatures at times. And if the boiler happens to come on under those conditions, we need to protect it against flue gas condensation. And this is one way to do that. This is called an anti-condensation valve. Caleffi makes these, SB makes these, Danfoss makes these. Basically, they're a high flow capacity thermostatic mixing valve. And in the lower right over here, just above the boiler circulator, you can see where that valve's installed. What this valve will do is when the boiler first starts or when cool water comes back to the boiler, it will create a recirculation through the boiler, and it will take warmer water coming out of the boiler and mix it with some of the cooler water coming back from the distribution system. And that thermostatic element will get that water temperature warm enough so that as it goes back into the boiler, it won't cause sustained flue gas condensation. It's definitely something you should consider if you're retrofitting cast iron, steel, or copper tube boiler. If it's a ModCon boiler, a ModCon boiler is designed to operate with flue gas condensation. You don't want to put one of these valves in. that would be counterproductive to what you're trying to accomplish with a condensing boiler. But many of the existing hydronic systems that are potential candidates for either a water-to-water heat pump or an air-to-water heat pump have what I refer to as a conventional boiler, a boiler that was not intended to operate with water temperatures that would cause sustained flue gas condensation. So again, this is another hydronic detail. Anytime you're evaluating a system, definitely take a look at this. And then finally, I said, here's your turn. I showed you a schematic, and I'll review it here. We've got 2 outdoor air-to-water heat pumps. It's a nice-looking installation, a nice-looking stance here. Here's a photo in the middle here behind the unit, and I'm sure most of you are saying, well, why didn't they insulate that hose? Well, I asked the same question. They need to come back and insulate that. But I'll tell you, that's not the issue I'm looking at here, okay? We've got a pipe that comes in from the building, and basically here it splits. We have one circuit through one of these heat pumps. These heat pumps happen to have an internal circulator, okay? So some of that flow goes through this circulator and it goes back over to the red pipe, and it's the same thing on this side. So it's basically almost like a mirror image. And the problem that I'm want you to think about, these 2 heat pumps are operated as a 2-stage unit, just like 2 boilers. We'd bring on one heat pump if the water temperature that we need is being produced by one heat pump. We don't need to turn the second one on. But if we have a large load, or if we have whatever conditions requiring a higher temperature or a higher rate of heat transfer, we're going to bring both heat pumps on. The problem occurs when only one of these heat pumps is on. And I'm going to tell you the answer here in the next slide, but I just want you to look at that, think about it a little bit. Again, it's like mirror images. We have a pipe here, we have a circulator, come back, and same thing over on this side. Okay, so I'm going to share the answer with you now. The problem when only one of these heat pumps and its associated circulator is operating is that some of the flow is simply going to short circuit through the other heat pump. The solution is to put a check valve in. Don't assume that if you happen to be working with a heat pump that has an internal circulator, don't assume there's a check valve there. So in this case, it was a pretty easy retrofit. A check valve was put in on both of these. So when one unit is operating, basically that prevents flow reversal through the other unit. And that flow reversal, let me just go back to the other slide. Let's say the heat pump on the left is operating. So this circulator is on, it's pushing flow up through here. Now we'd like to think all that flow is smart enough to go where it's supposed to go, into the building, and then it comes back. But that flow will see a path just like this in reverse. There's no check valve here in the circulator, and it'll simply come back and go right back into the heat pump. So this is what's going to occur. Not only is that going to take some heat away from that flow, it's going to mix some cooler fluid, because this is lost heat. Some of that cooler fluid is going to go back into here. So there's just nothing good about this. And fortunately, the solution is a check valve. And again, that was pretty easy in this case. But again, nothing wrong with the heat pumps. The problem with this job was simply the installer didn't understand that if one heat pump is on and the other one is off, without check valves in both circuits, we're going to have a flow reversal. This is the same reason that we put check valves into zone circulators. When only one valve or one circulator is operating and the other ones are off, we're going to get, without check valves, we would get flow reversal. Okay, so we've got about 9 minutes left, and Kevin, I'm going to turn it back to you. We'll do some Q&A.
Yeah, I've got some picked out here for you. The first one I have selected is, what are synergistic system arrangements for high domestic water heating loads with modest or small heating loads using geothermal?
Okay. So let's assume we've got a lot of showers, we've got a high demand for domestic hot water. Maybe that's in a building that has a really well done thermal envelope, so our space taking load is relatively small. This actually comes up a lot. It's come up for years. It's come up with boilers, and certainly modern, especially custom houses. This can be the case. There's two approaches to it. One is that you simply put more heat pumps in to build the capacity, and you can do relatively simple calculations to determine if, for example, the house needs 10 gallons a minute of domestic hot water at 120 degrees and you have 50-degree cold water. It's a pretty simple calculation, but it's a surprising result. Oftentimes you'll find you're into 300,000 BTUs per hour. A 5-time heat pump on a cold day is doing maybe 40,000 BTUs per hour. So you could add heat pumps to the system and simply build enough capacity. You could add a boiler to the system that would give you reserve capacity when there's a high domestic hot water demand. The other option would be to have reduced capacity, or let's say we just put one heat pump in. We'd have to have a lot of storage. We'd have to perhaps have several hundred gallons of hot water storage that could be sent out to that high flow load and then recovered over a period of several hours. There's pros and cons to both of those approaches. The one that I tend to lean towards would be to put a boiler in and use the boiler just during very high demand periods of domestic water. The boiler and the heat pump could both operate, but the boiler is giving you what I'll call the full afterburner approach to get that 200, 300,000 BTUs per hour into that domestic hot water.
Okay. Thanks, John. Next one. Why do heat pump manufacturers require a backup boiler?
Um, well, they don't really require it. There are mixed opinions on it. If we put a heat pump in, if it has the capacity to handle design load, why do we need another heat source? Is probably what the question is framed around. I like the idea of a backup heat source. Let me pose a situation. We have a heat pump. It's in a remote rural location. Let's say a lightning bolt hits the house or hits the electrical service leading to the house, and it fries one of the boards in the heat pump. I'll ask the question, can I get a new board in a day or two? Or is it a week or is it a month out? I didn't know the answer to that, but if that heat pump was the sole heat source in the system, and it's a week out, and if that week happens to be in the winter, that could be a very difficult situation. We have no way to heat the building. Other reasons to include a boiler. If it's a fossil fuel boiler, gas, propane, oil, if you have on-peak, off-peak rates, it might prove to be more economical to run the boiler during a very high on-peak rate period. We've seen rate structures up in Maine that vary from 44 cents a kilowatt hour on peak to 7 cents a kilowatt hour off peak. So those kind of very high peak rates, again, it might make sense to run the boiler. Fossil fuel boilers can operate on very small backup generators. It is possible to run a heat pump, even electric resistance heat on a generator, but it's a multi-kilowatt generator versus maybe a small tabletop generator that could run the burner as well as some of the zone valves or zone circulators. So there are good arguments to have a uh, dual fuel system, as we'll refer to it. We're still counting on the heat pump to do the majority of the seasonal energy. It could be upwards of 90, even 95% of the seasonal energy coming from a heat pump. So we are transitioning the majority of that load over. But I also recognize that actually have an existing boiler and it has service life left. Leave it in the system as backup, as supplemental heat, and potentially even something that could be coordinated with time of use electrical rates.
Okay. This next one is in reference to something he had previously said in last webinar, I believe. It says, in an earlier webinar, John had said that an Intertech heat pump can be used without a buffer tank in most situations. What are those situations?
Okay, definitely paying attention. Um,
Hanging on every word, John. Watch it.
uh, the only situation where I would still suggest that buffer tank would make sense would be where, and this is in regards to the WV or the AV systems, which are true variable speed heat pumps from Enertech. A scenario where somebody's using several panel radiators, all of which are controlled by thermostatic radiator valves. We have lots of very, very small loads. Let's just say we want to control them with thermostatic radiator valves. That is a common way to do panel radiators. We could simply draw from the TurboMax tank, and that could actually be a dual function device for us. It could be the domestic hot water tank, but it also could be a reserve mass that could supply, and we've designed systems that way. Um, so it's definitely the exception rather than the rule. But if you have any situation that creates micro loading and you don't have electrical feedback from your zoning method that can turn the heat pump on and off. Remember, thermostatic radiator valves are completely not electric. So we would still need to have some way to turn the heat pump on and off. Um, that would be the one exception where a buffer tank could still make sense. And again, I looked at the TurboMax tank, which is sold as part of that system as being a dual function tank under that situation.
Let's try to squeeze one last one in here, and then all the other ones we'll make sure get answered in our post-webinar email that we'll send via a PDF. But the
Okay.
last question I have, in radiant heat, can you compare between a mixing valve and an ejection system? What's the pros and cons of each?
Sure. Both can work. The choice of mixing device really kind of gets into the design of the system. And just a real quick kind of the history. Mixing valves were by far the dominant way to take higher temperature water and reduce the temperature to a very low temperature, let's say a floor heating system. Three-way valves were common with a motorized actuator, and even four-way valves were used. And the four-way valve, just if you're not familiar with it, the four-way valve is designed to have two mixing points, one to control supply temperature, the other is used to boost the boiler inlet temperature to prevent that flue gas condensation that we talked about. Um, Today, most boilers don't need mixing. They're going to produce, if it's a modulated condensing boiler, it's going to produce the water temperature without mixing. What you don't want to do with either a heat pump or with a ModCon boiler is provide or call it to produce a higher temperature only to mix it down before it goes to the distribution system. That's just wasting efficiency. You're forcing the machine that's producing the heat to go to a higher temperature and operate at a lower efficiency only to blend it down. Injection makes sense when you have a high temperature difference between the heat source and the return water from the heat emitters. Case in point, let's say we have a boiler, we're producing 160-degree water, and we have return water coming back from a radiant floor at 95 degrees. That's a huge temperature difference between the hot water that's available to the mixing device and the cool water that's available to the mixing device. Under those conditions, we can use a very small circulator, literally something like a Takeo 007 or Crunch's 5058 circulator, and it could potentially provide the mixing for a system that might even be 2 or 300,000 BTUs per hour at design load. The reason for that is that high temperature difference. So in the context of heat pumps, I will tell you, first of all, most systems don't require any kind of mixing, valves or injection. If you're using a heat pump and you're, for whatever reason, producing high temperature water with that heat pump, maybe it's an off-peak system and you're producing, I'm picking a number, 150-degree water, and you're going to a low temperature floor. Yes, mixing can work. And either a three-way motorized valve or a variable speed injection pump. Either of those can work in that situation. One last thing, when you're dealing with large commercial floor heating systems with conventional boilers, let's say we want to move anywhere from 500,000 to maybe 1,000,000 BTUs per hour. Injection mixing tends to be less expensive from a hardware standpoint. In those size systems, we get up into 3-way and 4, I'm sorry, 3-inch and 4-inch pipe sizes and mixing valves, and those pipe sizes get very expensive.
Awesome. Thank you, John. If you want to give a sneak peek of the next month's webinar, that'd be great.
Will do. Yeah, so next month, we're going to do another topic that I think is especially relevant with heat pumps. We're going to look at the effect of tubing depth in a heated concrete slab. I'm bringing this topic up because over the years, we've had installers and masons say, what difference does it make if I just leave the tubing at the bottom of the slab versus either tying it to rebar or lifting it from welded wire fabric during the pour? We actually did a pretty deep analysis of that using finite element analysis. And I can assure you, it does make a difference temperature-wise to leave the tubing at the bottom of the slab versus roughly halfway up through the slab. And I won't give you a specific number because I want you to come here next May to tune into it. But I can tell you it is going to have a noticeable effect on the seasonal COP of either a geothermal water-to-water heat pump or an air-to-water heat pump. So I want to show you how much of an effect and show you, yes, it does make a difference. And these are some details to keep that tubing where it needs to be in the slab. So that's coming up on May 22nd.
Okay, awesome. That's going to do it for us today, guys. Thank you for joining us. Don't forget to sit tight if you can, just for a moment to fill out the survey. Again, that's the only way we can make improvements is from hearing from you guys. You'll be receiving an email. I know some of you guys have asked, but in that email, it's gonna come in the next coming days. But it'll have the Q&A, presentation slides, a copy of this video, as well as a link to register for the next month's webinar. Don't forget to pass that link along with any friends, family, or colleagues that you think would benefit from this webinar. Otherwise, have a great rest of your day.